Okay, this is sample problem 17.5. It says to calculate the pH at the equivalence point when 25 milliliters of 0.100 molar ammonia NH3 is titrated with 0.100 molar HCl. Equivalence point, okay? Okay, so this looks like a really simple problem. There's not very many numbers in there, so it looks pretty simple, but it turns out it's a little bit involved. So here's what we're claiming. Since this is the equivalence point, and the volumes are in milliliters, so I'm going to make the following claim. The millimoles of ammonia are equal to the millimoles of HCl. That's what the equivalence points, where the number of moles or millimoles are equal to each other. We know the volume and the molarity of ammonia, so let's figure out what that number of millimoles is. 25 milliliters times 0.100 moles per liter. So that's going to give us 2.5 millimoles. Okay, and that would be true for both of them, right? It's the equivalence point. They're equal to each other, so they're both 2.5 millimoles. But that's got to be equal to the volume of HCl in milliliters times its concentration. Well, they did pick the same concentration, so that makes it pretty easy, right? 2.5 millimoles divided by 0.1 mole per liter is going to give you the volume of HCl, and that's going to be 25 milliliters. Okay, so now we know the volume of HCl is 25 milliliters. We want to find the pH at that particular point. Okay, so what we're going to do is we're going to say, hey, this is a reaction of HCl, strong acid, with ammonia, weak base. Acid, so the H plus goes in this direction, so you get ammonium, NH4 plus, and chloride, Cl minus. Okay, the number of millimoles that are reacting are 2.50 for each of these. These start as 0. We subtract 2.50 from both of the reactants and add 2.50 for both of the products. So now, once the reaction is done, oh, by the way, I wrote that as a double arrow. That should not be a double arrow. It should be a single arrow because HCl is a strong acid. If one or both of the reactants is strong, it's a single arrow, meaning that it goes to completion. No equilibrium to be concerned with. So these are both 0. This is 2.5 millimole. So is this. However, this is the conjugate base from strong acid, which means we can ignore it. Don't worry about it. No effect on the pH. Ammonium, on the other hand, is the conjugate acid from a weak base. So that means it does affect the pH. So we do have to have that. So now what we're going to do is we're going to say, hey, conjugate acid. So ammonium, let's find out its concentration. It would be the number of millimoles divided by the volume. Now notice the volume is 50 milliliters, right? 25 plus 25. So now that would be 0.05 molar. So ammonium has an initial concentration of 0.05 molar. So what do we do with that? Ammonium is a weak acid because it's the conjugate acid of a weak base. So that means it reacts with water. This would be reversible to form hydronium and ammonia. Okay, so a second reaction is going to take place here. There's actually 2 reactions taking place. The titration, then once you get the equivalence point, once you get your product, which is the ammonium ion, that's going to react with water in a second step. And it's going to do it with a concentration of 0.05 molar. Minus x plus x plus x, right? Q is less than K. So 0.05 minus x, x and x. So let's come back up. Let's make some room. Oops. Again, I got to do this piecemeal sometimes. Okay, so Ka is equal to x squared over 0.05 minus x. So that means we can approximate this as x squared over 0.05. Here's what our Ka value is. We know that the Kb for ammonia is 1.8 times 10 to the minus 5. So that means the Ka for ammonium is Kw over Kb. So 1.0 times 10 to the minus 14 over 1.8 times 10 to the minus 5. I looked that value up. They don't give it to you here. You have to go all the way back to chapter 16 for the Kb values of weak bases to figure this out. And you get 5.6 times 10 to the minus 10. Okay, there you go. There's our value there. So that means that this is equal to 5.6 times 10 to the minus 10. So that's where we're at right now. So again, notice how much space and effort and calculations this takes. These are some of the most challenging problems in chemistry, really, quite frankly, for general chemistry anyways, are doing these pH calculations of titrations, especially if one of them is a weak acid or base. Okay, so the reason we're doing this is because we're trying to find out what X is. X is the concentration of hydronium. So we got to find X. So X squared is 0.05 times 5.6 times 10 to the minus 10. So let's go ahead and put that in there into our calculator. 0.05 times 5.6 times 10 to the minus 10. 2.8 times 10 to the minus 11. So X is the square root of that. (5.29 times 10 to the minus 6). pH, negative log of that. Putting everything together from chapter 16 and from 17. 5.28. There you go. There's our pH. So at the equivalence point of HCl and ammonia, strong acid with a weak base, the equivalence point is acidic. Now that makes sense. If we have a strong acid and a weak base, the equivalence point should be in the acidic regime. So there we go.